Good morning. Most of today's class is going to be a work period, as I promised you, but I also did say that I would expect you to have the rest of the notes from 3.6 complete and some understanding there, because starting Monday morning, we're moving forward. So without further ado, here we go. First off, I'd like you to find this page in your notes. It's about halfway through the 3.6 notes section, where I have a typo. It's not so much a typo as old chemists do things differently than modern chemists do, and apparently I am now an old chemist. In this section here, group 1 refers to your alkali metals, and group 2 refers to your alkali earth metals. So that's the sodium column and the calcium column, respectively. Group 7 there should have been group 17, i.e. the halogens, fluorine, chlorine, bromine, etc. And I'll show you why that becomes important in just a moment here. But please, everyone, make that change now. What we're doing now is writing our dissociation equations with acids and bases. And I believe you all had a chance to copy down the examples that I had from Tuesday's. However, I'm going to give you a couple more just to show what I mean, so that those people who are on the physics trip can see this talked out in real time. So, for writing the modified Arrhenius equation for the following substance to help explain why each is acidic or basic, for butanoic acid. So first thing I know is that they've given me the formula. If they didn't, I would go to page 8 in my data book and look it up. But here it is, C3H7COOH. This COOH complex tells me it's an organic acid. I've talked with a few of you about that, what that means. Mostly, though, I just need you to look it up in the data book, copy it down, and also look at the same column on that row where you will see this chemical. This is butanoate ion. And this is what you get when you strip off that hydrogen off the butanoic acid. So I always have my reactant, I have water, and a reaction arrow. Those three pieces are universal. After the reaction arrow, I will either have hydronium ion or hydroxide, depending on whether I have an acid or a base. Today I've got an acid, so I have hydronium ion, H3O+. Then to balance my equation, I see that my water has stolen one hydrogen away from the butanoic acid. If I draw that in here, let's use purple. This guy has been scalped by the water. So now I am left with C3H7COO, -1 charge. Charges are crucial. Must have that. And if you'll notice, my total charge on this side is 0. And my total charge on this side is actually also 0. +1 and -1 add up to give me 0. Next example, lithium phosphate. So lithium, we can ignore because it is group 1. And forgive me trying to write here with my mouse. Group 1. There we go. So I can ignore the lithium and just write phosphate ion, PO4, 3-. Add my water, have my reaction arrow. Today I have a base, so I have hydroxide. And in this case, one of my hydrogens has left the water, run off to join the circus, and joined the phosphate. I now have HPO4, 2-. Last example, zinc hydroxide, where I do not tell you whether it's an acid or a base, but I'm hopeful that by now you recognize that things with hydroxide ion are bases. Now, this OH is an ionic anion. This OH is part of an organic acid, that COOH compound. Please do not confuse those two. But if you have a metal cation and a hydroxide, you're going to have an ionic base. So zinc with hydroxide dissociates just as I showed you in the previous section, 2 hydroxides and 1 zinc. Slight change or slight nuance to add. If your substance is a non-metal oxide, so carbon and sulfur are non-metals, they have oxygen attached to them. We're going to double up on the amount of water. For example, Carbon dioxide reacts with water one time to form a complete compound of H2CO3 aqueous. Our STEM said carbon dioxide is a major air pollutant from the combustion of fossil fuels, suggests a possible chemical reaction that explains the acidity of a CO2 solution. So here's your first step. Carbon dioxide and water gives you H2CO3. And if everybody were to look that up on their data table, they would find that H2CO3 represents carbonic acid. Okay, so now we know this is definitely an acid. H2CO3 reacts with water. So here's where I said you need 2 water molecules. Here's the second to give you hydronium ion and hydrogen carbonate ions. Look at your next section where you have the example of sulfur dioxide. Pause for a moment and see if you can figure out how sulfur dioxide would react. And I would ask your substitute teacher to pause the video for a moment here. Okay, we're back. And sulfur dioxide, also a major air pollutant, also acts in acid rain production. And we notice that it is reacting exactly the same way the carbon dioxide did. Sulfur dioxide with water gives you hydrogen sulfite ions, which react with a second water to give you hydronium and hydrogen sulfate ions. Hydrogen sulfate aqueous, hydrogen sulfate ions. Again, the charge is critical. New piece, and this is not in your notes, so I've provided a printout of these 2 slides for everyone in the class. Some of the acids on your periodic table or on your data table are called strong acids. Strong in this case doesn't have anything to do with concentration. Strong means that they will react 100%. That of all my hydrogen chloride molecules, they are almost all going to ionize. This reaction is complete. That should be like a really heavy arrow there, which I'm screwing up the drawing of, but you get the idea. So they have a very low pH in solution. They're very strongly acidic. They are really good at conduct electricity. They've got a really strong reaction with metals. And most of the ones that we're going to work with in Chem 20 are strong acids. You get to working with the weak acids in Chem 30. So don't stress too much over them right now. Anything below hydronium on this table is considered a weak acid. So from hydronium on down, and that includes all of page 9. Okay, they do not ionize completely. So here I have sulfurous acid right there, reacting with water to give me hydronium and hydrogen sulfate ion. But notice that my arrow here is double-headed. This reaction flip-flops back and forth. And really only less than 50% of the molecules are actually going to ionize. So for example, if I've got 1 mole of hydrogen sulfite molecule, I'm going to end up less than half a mole of hydronium ions. So that means that their pH is still acidic, still less than 7, but not nearly so much less than 7. It'll be in the 5 to 6 range. They're less conductive, and they don't react with metals as strongly. So this is relevant to question number 1 on your workbook. Okay, rushing ahead here because I'm almost at my 10-minute mark. Neutralization is a reaction. It's double replacement. Acid and base gives you an ionic salt, an ionic compound, and water. Your products are always neutral. And I have linked to you a Professor Dave Explains video that I'd encourage you to go watch. He does a pretty good job of laying it out. When you neutralize things, you always get water. Your hydronium reacts with hydroxide, yoinks that 1 extra hydrogen away, yoink, and we get 2 water molecules. I would also encourage you to watch Crash Course Chemistry number 8, which is about acid and base reactions and why we treat with acid spills and base spills the way we do. Thank you for your time. I